Welcome everybody. Okay, so now we're gonna start analyzing this notion. It's gonna be our central notion of the notion of satisfiability. So let's recall like all the objects that we have so far. So tau is usually denote the vocabulary, which is where it defines the symbols that we can use. That tells us exactly which symbols we can use. For instance, we talked a lot about the vocabulary of groups has a constant and an operation. In here, we're going to use M to be a tau structure. For instance, the additive group of the integers. Let phi be a formula. So this thing up here, the part in red, is a formula. And we always need these variable assignments that we're going to simplify later. But we need them for the formal definition so far. Which is a map that assigns element of M to each variable symbol. But you only care about the symbols that you're actually using. You don't care about all the symbols, but about the ones all the variable symbols, but the ones you're using, you have to assign something in M. For instance, the variable X, maybe you assign 2, the variable Y, maybe you assign 3 in this particular example. And we defined in class what this symbol means. Here I was missing the S, the variable assignment. And recall that we read this symbol as saying that the structure M satisfies the formula phi with S, where S is the variable assignment. Or we can read as the formula phi is true in M according to the variable assignment S. Or M and S model phi, or add a model are a model of phi. Okay, so all those ways, this is the same, there are different ways of saying the same thing, saying this thing up here. And it's going to be our central notion. Recall that we had this theorem that said that whether phi is true in M according to S depends only on the value of S of X for the free variables of phi. Okay, so the free variables of phi are the only ones we need to know what value they have before we decide whether the formula is true or not in the structure. The ones that are not free, it doesn't matter what S is telling us. So, for instance, if phi is a sentence, recall that means that it has no free variables, then whether phi is true in M according to S does not really depend on S, because there is no free variable, so there is nothing you need to figure out beforehand. Okay, so when S is a sentence and it has no free variables, in that case we're gonna write this as opposed to what we did before, which had the S up there. So we don't need the S, the variable assignment, if our formula is an actual sentence without free variables. And in that case, we can cross out all these parts. All right. So in that case, we're gonna just read like M. The structure M satisfies phi, or we're gonna say phi is true in M, or M models. In that case, it has to be plural. Phi, or M is a model of phi. Okay. So that's what this symbol means now when we have a sentence, because we don't have to worry about free variables. So we don't have to worry about the variable assignment. We still, to know what that means for a sentence, the recursive definition still needs to use variable assignment. So we cannot avoid variable assignments completely. They're needed for the definition. Okay, so one last definition is a new definition. If you have a set of formulas or sentences, whatever you want, but now it's a set, it's not just one, but it's a set, which might be finite or might be infinite. Then we use the same notation, but now we put the set here, formulas, to mean that each of the formulas in the set is satisfied in M according to S. Okay, so for all phi that belongs to that set of formulas, phi satisfies M according to that variable assignment. Okay, cool. So let's just see some examples to get used to this notion of a formula being satisfied, or a set of formulas being satisfied in a structure. For instance, you remember from your algebra class that a group, what is a group? A group is a structure that has a domain and a constant symbol and an element that is a particular element, identity of the group, and an operation. So we have the particular vocabulary with a constant symbol, naming identity, and an operation symbol, so a function symbol. So that's the vocabulary. So it has these two things: E is a constant symbol, and star and all times is binary function symbol. And the group needs to satisfy these three sentences. Okay, so it's a set of three sentences that to have a group, in order to have a group, you need to satisfy these three sentences, and you remember what they are. They are, the first one tells you associativity of the operation. The second one tells you that the identity should behave like the identity. X times E equals X for every X. Actually, you should also add E times X, like the other way, equals X. And we have an inverse statement that says that for every X, there exists a Y, such that X times Y is the identity. So the Y is the inverse of X, right? So these three statements, if you satisfy those, then you're a group, okay? So let's look at another example. I don't know if you have seen this one before, but a linear ordering is just a structure again. Now, in the vocabulary, which has only one symbol, this symbol right here, where the symbol is a binary relation symbol, the textbook calls them predicate symbols. And the structure, this relation up here, less than sub k, is the one that is interpreting the symbol here. And the structure needs to satisfy 4 axioms. They are called axioms. And the first one is transitivity, which tells you that if x is below y and y is below z, then x is below z. Anti-reflexive, that tells you that nobody is strictly below itself. Anti-symmetric, that tells you that you cannot have x strictly below y and y strictly below x at the same time. And also they satisfy the trichotomy, that tells that for any two elements, either x is below y or y is below x, or they are the same. Those are the three only possibilities. That's going to make it a linear ordering. So that's the word linear comes because in this ordering, all the elements are ordered in a line. Whenever you have two elements, one is bigger than the other. Okay, so that's any structure that satisfies these axioms is going to be called a linear order. You don't have to remember all these axioms, by the way. I'm just showing you examples of how these things show up in mathematics. Here is another interesting one. An order field is a structure in the vocabulary that has these 5 symbols. So it's a structure with an interpretation for each of the symbols. So 0 sub k is interpreting the symbol boldface 0. 1 sub k is interpreting this one. The actual plus sub k is interpreting this symbol. And times is interpreting this one. And this less sub k is interpreting this symbol curvy less. And what do we need? So here we have that 0 and 1 are constant symbols. The O plus and O times are binary function symbols. So they are operations that take 2 inputs and output one thing. And less than is a binary relation symbol. So it takes 2 things and then outputs whether it's true or false. So these 2 things satisfy this relation. And there's a lot of axioms. I'm not going to go through them, but a lot of axioms. And if you satisfy all these first order formulas, then you are said to be an order field. Do we know one example of an order field? I mean, this is a lot of properties, but we know some examples. We know 2. We know the rationals. Rational numbers are a field, and the ordering among them makes them an order field. And the real numbers. The real numbers are also a field, and the ordering among them makes them an order field. The complex numbers are a field, but they are not an order field. It's not a way to put an order among all the complex numbers in the plane to make it an order field to satisfy the properties that the order plays well with addition and multiplication. So, okay, so here are some examples of how these first order formulas can be used to define classes of structures that are used in mathematics. Here I'm going to give you now 2 more examples where first order formulas are used not for algebra, but as a foundation for mathematics. So there are two very famous. One, list of axioms. Again, you don't have to memorize this. I'm just giving you examples so you guys see how these things are used. So the Peano arithmetic axioms are a list of axioms trying to axiomatize the numbers, the natural numbers. They're trying to set down the basic properties of the natural numbers that then you can use in proofs about them. The first axioms here say that the natural numbers are a discrete semi-ring. They are not a ring because they are integers are a ring, because you need inverses for addition, and you don't have that in the naturals. So you have half of the integers, and that's why it's a semi-ring. So half of the ring, more or less. And then, so don't worry about what they say exactly. And then they have an axiom scheme. So it's a list of axioms, one for each first order formula phi. And for each formula phi, we have an induction axiom for phi that tells you that if phi is true in 0, and for every x, you can prove that if phi is true at x, then it's true at x plus 1, then all these together tell you that for every x, phi of x, right? So that's the induction axiom for this formula phi written in one line. And in Peano arithmetic, you have one such axiom for each formula phi. So actually you have infinitely many axioms, because there are infinitely many first order formulas you can write in this vocabulary. Okay, so these are the axioms for very famous axioms of Peano arithmetic, which are trying to axiomatize the natural numbers so you can prove everything you want about the natural numbers from them. But as we're gonna see later, not yet, they don't give you everything you need. There are things that are true about the natural numbers that you can write in this first order language that is not that complicated, and you can still prove from Peano axioms. Actually, the Peano axioms are pretty good. Actually, like great majority of mathematics or number theory, you can prove using just Peano axioms. But every so often there are things that need you to go beyond. And last, let me mention set theory, because this is the basis for all of math. Like the previous one was just for the numbers, natural numbers. In set theory, you can develop all of mathematics. I don't want to go into the axioms, but essentially, set theory, the vocabulary is only one binary symbol, relation symbol, so predicate symbol, belongs. And everything in set theory represents a set. So everything, and the elements of the sets are sets themselves, which have elements themselves, and you build out of the empty set, you start building sets, and you build a whole large structure. Here I wrote down the first axioms, skip the other ones, so don't worry about what they say. But the interesting thing about this just list of few axioms is that all the mathematics that you learn in all your undergrad courses, you can develop here. Again, this is not everything is going to follow from these guys. So there are things that we can prove just using Zermelo axioms, Zermelo-Frankel axioms. And the story there gets a bit more complicated, because in the previous case I told you, well, there are things that are true that we can still not prove in Peano arithmetic. How do we know they are true? Well, because we can prove them in Zermelo-Frankel. But once there is something you're going to prove in Zermelo-Frankel set theory, then what does it mean for it to be true if you cannot prove it? Well, you have to find other arguments, mathematical arguments, or it's not even clear what it means. But I mean, there's definitely people trying to think of what does it mean for things that cannot be proven in ZFC to be true or false, and what should be true. But most of mathematics that you learn, usually, like the great majority, 99%, can be proved inside this system of set theory. And it's just a first order system, first order logic, the way we defined it last week. Only one symbol, you develop natural numbers, rationals, reals, complexes, functions from integers, from reals to reals, differentiable functions, manifolds, everything you can develop inside here. Cool, so then there are kind of two types of applications of these first order formulas and first order logic. One is like Peano arithmetic and Zermelo-Frankel, where you use them as foundations for mathematics. You try to build mathematics from this thing and see how mathematics works. And there are the more algebraic outlook, which is we consider particular kind of structures, order fields, linear orderings, or groups, or we're gonna see like many classes of structures that are not where your interest is not to develop a basis of mathematics, but is to study a particular kind of structure. And we're gonna want to, in the rest of the course, what we want to do is kind of do that, because our goal is to understand a little bit more about how this first order logic works. And there are two main theorems, compactness and completeness, that we're gonna spend quite a bit of time on them. And we're gonna see how they work in the algebraic setting. So we are gonna be playing with this algebraic setting quite a bit to kind of see how the functioning of the logic itself. And if you want to see how to develop mathematics from this, then you should take 135 at some point. Or you could also go to the playlist, my other playlist for the videos for 135. And there I do the whole development of Zermelo-Fraenkel set theory. Well, I'm doing it right now. So let's make a general definition that encapsulates all these examples. If you're given a set of well-formed formulas, which are actually sentences, we call mod gamma, mod for models, be the class of all structures which satisfy all the sentences in gamma. Okay, so for instance, if gamma is the axiom for groups, do you remember those three first order axioms, those first order sentences? Then mod gamma is the class of all groups. Okay, so gamma here is a list of axioms. So gamma is a set of strings of symbols, and mod gamma represents all the structures that model those axioms. Okay, so that's the difference between the axioms for groups and the class of all groups. And so in general, if you have a class of structures, all in the same vocabulary, we are gonna say that the class is an elementary class. If there exists a well-formed sentence, phi, such that this class is exactly the models for phi. Okay? So for instance, if we take the axioms for groups, remember they have three axioms. There are three separate ones, and here we want just a unique one. Well, that's not a real issue, because we can put the three axioms together with an and in between. First axiom and second axiom and third axiom. We get one long axiom that has the three of them together, right? So we can write a single sentence, single first order sentence, whose models are exactly the groups. Okay, so the class of groups is an elementary class. The same for the class of linear orderings, it's elementary class. The class of order fields, it's an elementary class. So all of those are elementary classes. Another notion that we're going to see is weakly elementary classes. So a weakly elementary class is one where you have a set of formulas, and the class is exactly the set of all the models of that, the class of all models of that set of formulas. Okay, so if you have finitely many formulas in your set, again, you can just put them together with ands, and actually you obtain an elementary class. So weakly elementary classes are going to be actually weakly elementary classes are not elementary when this set gamma is infinite and there is no way to make it smaller. Okay, so the axioms for piano arithmetic, we said the example that we showed, there are infinitely many axioms right here, because for each formula phi we have an induction axiom for phi. So actually this set of formulas is an infinite set of formulas, and it's not equivalent to any finite subset. So you're going to represent all these infinite formulas with a single one. So the class of models of piano arithmetic is going to be a weakly elementary class, but it's not going to be an elementary class because there is no single formula, that axiom that puts all this together. The natural numbers are going to be one structure inside the class. We hope, the hope was that these axioms for piano arithmetic actually characterize the natural numbers, But as we're going to see later in the course, they don't. There are actually other structures that are not the natural numbers, but still satisfy all these axioms that we hope to axiomatize the natural numbers. So that means that this set of axioms is not really as complete as we want, because there are some things, we have other structures that we don't want in there, they still satisfy it. For instance, let me show you another example of a weakly elementary class. So let's consider the class of infinite groups. We want to avoid the finite groups and just consider the infinite groups. And we want to consider a set of sentences whose models are exactly the infinite groups. So what are we going to do? What is going to be the set of sentences? So this is going to be the group axiom 1, group axiom 2, group axiom 3. Those are in the previous slides. So these are the 3 axioms for groups. So together, if something satisfies those 3 axioms, it's a group. And then we are going to add all these sentences. I'm going to call them now phi sub n, just for today, and in the natural numbers. So we're going to have infinitely many sentences, one for each natural number. And the idea is that phi sub n is going to say that the structure has at least n elements. Okay? So it's going to say that there is at least n elements. So it's going to say it exists x1, x2, up to xn, such that they're all different. So we have to put all the combinations of x1 and x2 on x1, x2, x3, up to xn, and say that they are all different. x1 different than x2, and x2 different than x3, x3 different than x4, and all of them. All the possible combinations of these variables so that they are all different. So this formula phi sub n says there exist n different things. So the universe of the structure has to have at least n elements or more. So if you put them all of them together for all the n, the only way to have that is if you have an infinite structure. All right. So this gamma right here is an example of a infinite list of axioms, which you cannot reduce to finitely many, and that requires a little proof. Whose models are the infinite groups, so showing that the infinite groups are a weakly elementary class. And they are not going to be the groups by themselves, like a class of all groups containing finite and infinite, those are an elementary class. But if you want to restrict yourself to the infinite, you need to add infinitely many more axioms, making it a weakly elementary class. Alright, we'll see more of these in the next videos. See you guys later.